Hello, my name is Neil Troutman. I'm a graduate student at Indiana University, Purdue University of Indianapolis, and I'm here to present to you our work on the chilled water system modeling and optimization that I submitted as my thesis with the help of Dr. Ali Razpan and Dr. Jay Chen. So the goal of this project was to determine the energy saving potential of optimizing different pieces of equipment in a chilled water system that are equipped with a variable frequency drive. In order to do this, we built an overall chilled water system model by linking together various component models in order to simulate the overall system operation. And additionally, we wanted to determine if there were any potential control strategies that we could use to control the variable frequency drive on the condenser water pump and on the cooling tower fan in order to achieve optimal operation. So here you can see our overall system model. It's a flowchart of our system model. It's comprised of 5 different component models: the cooling load prediction model, the condenser water pump model, the cooling tower model, the chiller model, and a mass and energy balance, which helps link all of them together. The inputs and outputs of each of these models affects the other models, which ends up helping to model the system as a whole. Additionally, we have user-defined inputs for the cooling tower fan and the condenser water pump, which we send through an optimization process in order to minimize the total system power. We performed our case study at the Idle-Droid Museum in downtown Indianapolis. It's a large facility with a strict internal climate in order to maintain the stability of the exhibits housed within the museum. The chilled water system is comprised of a 300-ton Carrier chiller, a 307-ton Baltimore Air Coil Company cooling tower, two 15-horsepower evaporator pumps, and a single 15-horsepower condenser water pump. Each of these pieces of equipment is actually already fitted with a VFD. However, the evaporator and the condenser water pump, the building automation system has no internal control logic to control these VFDs, so they operate at 100% year-round, regardless of any external or internal variables. So in terms of our data collection, we started on July 9th, 2019. We finished on October 31st, 2019. We used a sampling rate of every 15 minutes. In the table, you can see an overview of the data that we collected and the equipment we used. We used a combination of data loggers, current transducers, 3-phase power analyzers, a Fuji portable ultrasonic flow meter, some of the data we collected using the building automation system, and finally we got our weather data using NOAA quality controlled data sets. Here in this table, you can see an overview of our modeling process. For our cooling load prediction algorithm, we used a multiple nonlinear regression algorithm to predict the building's cooling load subject to a variety of ambient and occupancy related variables. For our condenser pump model, we used the NREL default curve method. For the cooling tower model, we used the NTU effectiveness method. For our chiller model, we developed a modification that combines the Gordon model, which combines 2 different modifications in order to incorporate condenser water flow rate as an input. And finally, we used principles of mass and energy balance to help link these models together and model the system as a whole. So for our condenser pump model, we use the NREL default curve method, which uses data collected at full load power from the condenser water pump and full load volumetric flow rate from the Fuji ultrasonic flow meter, as well as correlation coefficients provided by NREL in order to determine the flow rate as a relationship to an input power fraction. The relationship can be seen in the bottom left and under equation. Once we input our full load values, we were able to develop the graph to our right. The red line on the graph to right indicates the minimum flow rate that's allowed through the chiller in order to maintain turbulent flow on the condenser side of the chiller. Before we get into the cooling load algorithm, I wanted to talk to you about how we calculated the cooling load. The evaporated flow rate couldn't be collected due to the insulation covering the chilled water piping. So instead, we calculated the cooling load from the condenser water flow rate and the temperature difference on the condenser water side of the chilled water system by subtracting the chiller's power input from the load. The difficulty with that is we had a lot of noise in the data that we ended up determining. Small temperature differences across the condenser would result in really large changes in the cooling load calculation. So our solution to that was to use the 1-hour moving average of the discrete data points in order to minimize the noise in the data set. You can see the graph of both the discrete and the moving average of the cooling load on the right, which brings us to the cooling load prediction. Again, we use multiple nonlinear regression algorithm. The inputs include ambient temperature, relative humidity, solar radiation, the day of the week, occupied hours, and the cooling load 2 hours prior to the current data point in order to determine the cooling load. The equation can be seen here in the middle of the slide, along with the table which provides the coefficients from the regression of our collected data. Here are the results of our multiple nonlinear regression algorithm. The R squared of the algorithm was found to be 0.9302 with an RSME of 6.88 tons or 24.2 kilowatts. Before we get into the cooling tower modeling efforts, I wanted to talk to you about the measurements we took. We took, in lieu of true power measurements over long periods of time, we took three-phase power measurements at 25% fan speed, 50% fan speed, 75% fan speed, and 100% fan speed to create a relationship between the line amps and the fan power and the fan speed. That way we could determine the fan power just based on the amps, and we could take long-term measurements using just a current transducer and a data logger instead of a three-phase power analyzer. Furthermore, the fan speed variation with relationship to the wet bulb temperature ended up being important. So in the graph on the bottom left, we can see that the fan operates at 100% speed for most of the year, as long as the tower outlet water temperature remains above the set point of 65 degrees Fahrenheit, at which point the cooling tower fan would begin to cycle between its minimum and maximum speeds, maximum being 100, minimum being 25% speed, in order to maintain the condenser water temperature at the set point, around the set point of 65 degrees Fahrenheit. The difficulty with this is we had to remove a lot of data from our cooling tower model because the cycling of the cooling tower fan creates a non-steady state system, and we couldn't model that with the technique that we used. So instead, we had to use performance data that was published for the cooling tower that we were taking data from. The performance data was published by the Baltimore Air Coil Company, and you can see in the graph on the right that we used a combination of both performance data and data that we collected from the system. The advantage to using both pieces of information was that we were able to actually increase the R squared and RSME of our relationship, improving the accuracy of our model, because when we used the performance data alone, the NTU of the cooling tower model tend to be overpredicted. The results for our final cooling tower model can be seen in this slide. As you can see, the predicted outlet water temperature follows the measured outlet water temperature fairly well. The measured versus predicted tower outlet water temperature follows good correlation with low root mean squared errors. And that brings us to our chiller modeling. We used combined modifications of the Gordon-NG method. The original Gordon model is a thermodynamic relationship that ends up regressing variables that are hard to collect, including the internal entropy change, the rate of heat leaks to the environment, and the thermal resistance of the heat exchangers. We ended up incorporating two different modifications. The first incorporates variable condenser flow rate into the model. The second improves the model's accuracy for measuring the coefficient of performance for chillers equipped with variable frequency drives, such as the one we collected our data for. And that brings us to the condenser water temperature input to our cooling tower or our chiller model. Initially, the input was supposed to be the condenser inlet water temperature. What we found is in our modeling efforts that the relationship would cause the pump power to constantly go towards its lowest variable, which would increase the outlet water temperature to a point, while the condenser water inlet temperature could remain relatively stable. The difficulty with that is it's underpredicts the effect that the outlet water temperature will have on the chiller's performance. Some authors recommend using the condenser outlet water temperature for variable condenser flow applications. The graph for that can be seen on the right. We ended up deciding to use a combination of the two when we took the average of both the inlet and the outlet water temperature, which makes the relationship iterative with respect to both variables. So here you can see the combined modified Gordon algorithm that we created uses a variety of inputs to determine the chiller coefficient of performance. at which point you have to regress certain variables in the relationship, and then you can algebraically rearrange the equation seen in order to solve for coefficient of performance once you have regressed those variables. And here you can see the results of the algorithm that we generated. The R squared was found to be 0.8756 with a root mean square error of 0.1785 tons per kilowatt. Here are more relationships that we developed from the algorithm that we used, relating the chiller's efficiency to the cooling load using different inlet condenser water temperatures. The surface graph can be seen on the right, while certain line graphs for different outlet water temperatures can be seen on the left. Finally, that brings us to our mass and energy balance, which combines the model. These were pretty simple. We just used the load and the coefficient of performance to determine the chiller power, which would then be input to determine the outlet condenser water temperature using the chiller power, cooling load, inlet condenser water temperature, and the flow rate determined. And using these relationships, we were able to determine the relationship between the actual and outlet, inlet and outlet condenser water temperature. You can see the graph of those on the left. They follow similar patterns. And on the right is a relationship between the actual and modeled chiller power for a period of time during the data collection process, which also follows similar patterns. And that brings us to how we optimize the system. So we used a generalized reduced gradient algorithm, which is supposed to be used for smooth, constrained, nonlinear functions, such as the one that we were dealing with. The objective that we set to the optimization was to minimize the system's overall power demand by controlling the cooling tower fan speed and the condenser pump power. The constraints that were in the optimization were the cooling load determined through the cooling load prediction algorithm, the minimum and maximum fan speed, and the minimum and maximum pump power. The minimum in this case was to maintain turbulent flow through the chiller, and then also the ambient variables collected from the time point of the optimization. That brings us to our different optimization scenarios. So scenario one, we decided to not control either the condenser water pump or the cooling tower fan, run them both at 100% speed. Scenario two was the baseline scenario, their current control strategy, where they would cycle the cooling tower fan between 100% and 25% in order to maintain the condenser water temperature at 65 degrees Fahrenheit. Scenario three, we decided that the condenser water pump speed would run at 100%, while the cooling tower fan speed would be optimized with the optimization algorithm. And finally, in scenario four, we decided to optimize both the condenser water pump speed and the cooling tower fan speed in order to try and minimize the total system power even further. Here are the results. So for the first 2 weeks, scenario 1 and 2 should actually be equal, since in the baseline, both the condenser water pump and the cooling tower fan ran at 100% until we reached October, at which point in scenario 2, the cooling tower fan began to cycle. As you can see, the scenario 2 is actually lower than the scenario 1, which means that cycling the cooling tower fan increased the efficiency of the system and actually saved them money, as opposed to running the cooling tower fan at 100% year-round. This slide compares scenario 2 and 3. So this is the baseline versus just an optimized cooling tower fan. As you can see, scenario 3 was consistently more efficient than the baseline from July all the way to October, excuse me. This would indicate that there is potential to save energy through optimizing the cooling tower fan. And finally, these graphs compare scenario 3 and 4. As you can see, there's practically no difference between the two, which would indicate that there is almost no advantage to optimizing the condenser water pump with a VFD. This would indicate that almost all the savings that can be achieved through optimization of both the condenser water pump and the cooling tower fan can be achieved through optimization of the condenser water cooling tower fan by itself. Here you can see the totals of the kilowatt hours that were used for each week and each scenario, with the table at the bottom indicating the percent savings versus the baseline. There was almost no difference between scenario 3 and 4, while October in scenario 1 had a much higher energy uses compared to the baseline. And this brings us finally to the proposed control strategy. Since there was no advantage to optimizing the condenser water pump speed, we ended up abandoning that as a potential control strategy, and we looked at how to control the cooling tower fan. So the graph on the left was the fan speed versus directly from wet bulb temperature. The correlation we found was rather poor, whereas if we controlled the approach temperature versus the wet bulb temperature, we had much better correlation, which would indicate that it's a much better control strategy for this situation. Thank you, and if you have any questions, I'd be happy to answer them.